Now, application of Gauss law. Application of Gauss law. So, with the help of Gauss law, we can determine the electric field of highly symmetrically charged body. So, it can be used to determine electric field due to highly symmetrical charged body. Highly symmetrical charged body. Why highly symmetrical charged body? Then only we will be able to make a proper Gaussian surface, so that at each and every point the electric field on that Gaussian surface will be 0. Just like see, first example we can say field due to point charge. Field due to point charge. Now, if we want to make a calculation of electric field due to point charge by using Gauss law, then we should make a Gaussian surface in such a manner that surface should be symmetrical about point charge. Means if we are making a spherical Gaussian surface, suppose we want to calculate the field at point P, which is r distance from the charge. So, I made a spherical Gaussian surface. A spherical Gaussian surface. So, what observe in that case? See, lines of forces like this. Lines of forces like this. So, if we are making a Gauss law or using Gauss law like this, total flux is equal to your E dot ds q enclosed by epsilon naught. See, if we are considering a small area ds, through this area, and since electric lines of forces and area in the same direction, the flux we can write here E into ds and area, total area, as well as q enclosed. How much q enclosed here? Q by epsilon naught. Then total electric field into area 4 pi r square q by epsilon naught. The electric field is equal to your 1 by 4 pi epsilon naught q by r square. This is the electric field due to point charge by using Gauss law. Similarly, see another case. Now, in the second point, field due to uniformly charged spherical conductor. Suppose this is your spherical conductor of radius r and having charge q. Again, in this case also, since our charge is symmetrically distributed throughout its surface, that's why we are able to calculate the field by using Gauss law, because we will able to make such a Gaussian surface in which each and every point will have that same electric field. So, here also we will make a spherical Gaussian surface. So, suppose we want to calculate the field at point P, and which is at distance r from the center of that sphere. So, if we are making a spherical Gaussian surface like this, this is a spherical Gaussian surface. Spherical Gaussian surface. So, here also lines of forces and area vector makes an angle 0. if lines of forces and area vector makes an angle 0, so then if we are using the same relation again, E dot ds is your q enclosed by epsilon naught. So E will be here, we have to calculate, and area your 4 pi r square q by epsilon naught. So E is equal to your 1 by 4 pi epsilon naught q by r square. This is the electric field, and since our point P is your outside point, we can say outside point electric field is given as 1 by 4 pi epsilon naught q by r square, q by small r square. Now, if we are having point inside, suppose we are talking about the inside point. See, for inside point, if this is your Gauss, this is charge body, and for inside point P, this is the Gaussian surface of radius r. So, okay, we can write here E into 4 pi r square, but how much charge enclosed by that surface? That is 0. So, E inside will be here 0. The inside value we will get a electric field 0, and outside these are the same type of result as we have found by using Coulomb's law. Next, third one, field due to uniformly charged non-conducting sphere. Non-conducting sphere. Now here our sphere is like this, a sphere of radius r, and charge is q. Now, due to this, if we want to calculate the field, so see, first for outside point. First for outside point, so we will make a Gaussian surface, and which will be your spherical Gaussian surface. Suppose we want to find the field at point P. And this is at distance r, in the same way as we did in the previous case. So, E into 4 pi r square will be your q enclosed by epsilon naught. So, E outside 1 by 4 pi epsilon naught q by r square. So, this is for outside point. Now, if we want to find for inside point, to see, second case for inside point. For inside point, we have to make a Gaussian surface like this. Suppose point P is here. We are making Gaussian surface like this of radius r. So, this much is charge, only enclosed charge, although charge is everywhere, but we have to see the only enclosed charge here. Again the same method, E dot ds is your q enclosed by epsilon naught. So, see the value of E here, area 4 pi r square. Now, q enclosed. Total charge in volume is your q by 4 by 3 pi r cube, and charge in this volume only 4 by 3 pi small r cube we can write. And now, simplify this one, the E inside you will get 1 by 4 pi epsilon naught q r by r cube. This is the field at inside point. So, what we observe, in case of non-conducting sphere, electric field at inside point is directly proportional to r, and outside point was inversely proportional to r square. E is proportional to 1 by r square, while here E is proportional to r, and this is the position capital R, and this point can be written as 1 by 4 pi epsilon naught q by r square. This is electric field due to uniformly charged non-conducting sphere.